Okay, big day today. One of our last big days of the year, actually. I'm going to take a few ideas and let them sit in the air for a little bit and then bring them all together towards the end. We take a bunch of these ideas and piece them together to make some big, awesome new creation of an idea, kind of like a Megazord, for those of you that know your Power Rangers. The first thing we'll talk about is radians and degrees. And the idea here is really reference angles. So we've talked about radians and degrees. If I have this angle here, well, I didn't draw that very well, so let me grab an actual line. If I have this angle here, let's say that that is, well, I'll see what it looks like. It's about, say, 140 degrees. Well, if it's 140 degrees, that means that this little piece here is 40 degrees. And what a reference angle is, the first idea is reference angles. What a reference angle is taking the little piece off the x-axis, always off the x-axis, and copying it to the other portion of the graph. It's taking an angle and putting it in the first quadrant. I can take all angles and compare them to angles in the first quadrant, and that's called a reference angle. So for example, this angle here, actually let me change where that is a little bit. Let's put it way down here. This angle might be something like, well, 90, 180, 270, 280 or so. Let's say this is 280 degrees. Well, that means that this little piece in here is 80 degrees. And so if I take the angle from the x-axis to my reference, or to my terminal side, to this point here, if I take that angle and copy it into the first quadrant, I should draw better than that. This angle here is also 80 degrees. That's called a reference angle. And the idea is taking some angle you have and getting its corresponding piece in the first quadrant. We'll talk about that a lot in the future. The second idea, and this is one that should be pretty apparent but is very important. If from the center, or from the origin of a coordinate plane, I travel right 5 units and up 3 units, where is the terminal point? Meaning, at what point do I end? Well, obviously from here, if I travel right 5 and up 3, I end at the point 5, 3. And we know that, but we want to start thinking about coordinates as distances. When you have an x-coordinate, that really means you have a distance from the y-axis. And when you have a y-coordinate, that really means you have a distance from the x-axis. So x and y coordinates are distances, and we've got to think of them that way. What if instead of being given 2 distances from the origin, I was given an angle and a total distance? Could I find this coordinate? So suppose I have this coordinate, and I know that the angle here was 50 degrees. Suppose we were given that. Could I find this point, x, comma, y? Well, the way that I would find that point is I would want to think about those distances again. So I think about this triangle down to the x-axis. I do the triangle to the x-axis because that's going to give me my width, my x variable first. And that's kind of like our idea of reference angles again. It's always the length to the x-axis. Well, now I'm trying to find the height y and the distance x. To find the distance x, I have a right triangle, and I have, if this is my angle theta, I have an adjacent side. If this is my angle theta, I have an adjacent side and a hypotenuse. So that means I'm going to do cosine. X is really the cosine of theta. Let me do this way. The cosine of theta is going to be adjacent over hypotenuse, or x over 3. So 3 times the cosine of theta gives me my x-coordinate. And I can calculate whatever that is. And theta in this case was 50, so 3 times the cosine of 50. I'm going to make sure I'm in degrees, and I am. 3 times the cosine of 50 is 1.92. So my x-coordinate is 1.92. Now I've got to find the y-coordinate. Well, now I've got sine This is the opposite side, and this is still my theta. So the sine of 50 is going to be y over 3. So 3 times the sine of 50 equals y. .3. So this is basically the point 1.92 comma 2.3. 1.92 comma 2.3. So I can find that coordinate knowing just an angle and a length. Really, if I took the process of using sines and cosines, I could find any angle. It wouldn't just have to be this theta of 50. It could be any angle at all. I could find any angle measure that I wanted to. And so to make this process easier, we always can think about having a radius of length 1. Since I can find any possible angle, I could really take this angle. Well, I can't adjust this one now, so I'll draw a new one. I could really take that angle and slide it to meet any of these measures. I could do any of these angle measures. So there's really a whole circle of possible coordinates I could find. So to find those possible coordinates, we always think about having a circle with a radius of 1, just because that makes everything easier. So we travel a distance of 1 unit from the center, and that's called the unit circle. So this circle we have right here is called a unit circle because its radius is 1. The third important idea is special right triangles, which we've talked about briefly before. But I'm going to give us 2 triangles that we're going to solve, and they both have a hypotenuse of 1. One of the special right triangles is a 45, 45, 90. Well, if it's a 45, 45, 90, we know it's isosceles. So if I call this length x and this length x, I have x squared plus x squared equals 1, which really means that 1 squared if I'm doing the Pythagorean theorem, and 1 squared is 1. So this is a squared and b squared is c squared, where a and b are both just x squared. So it's really 2x squared equals 1, so x squared equals a half. So if I come up here, that means that x equals the square root of a half. And I can square root 1, so that simplifies to 1 over the square root of 2. I can't have that radical on the bottom, so it becomes root 2 over 2 because I did this. So this length here is really root 2 over 2 and root 2 over 2. So a 45, 45 right triangle has that ratio. Root 2 over 2, root 2 over 2, and 1. The other special right triangle is a 30, 60, 90. Well, a 30, 60, 90 is actually just half of another isosceles, or of another isosceles triangle. If I take this triangle and I clone it, and I take my new triangle that I just drew and I flip it, this is also 30 degrees. And so this has a segment of length 1. And now I can think about doing the same isosceles triangle here. This is 30 and this is 30. And so up here is a total of 120. Sorry, bear with me. I flipped that in the wrong spot. I don't want this thing here. I want this triangle to be here. That's what I was looking for. My apologies. So really, if this length is 1, this length is 1, because these are both 30s, and this is a 60, so now we have an equilateral triangle where it's 60, 60, 60. So this is of length 1. Everything on this triangle is of length 1. Well, then this little piece here is half of that. So this actually has a length of a half. And that's how we can get the ratios for the rest of our special right triangle. I'm going to get rid of this extra triangle that we had over here. And I can do some Pythag if I do 1/2 squared plus b squared and have it equal c squared, which is 1 squared. I get 1/4 plus b squared is 1. Subtract a 1/4 from both sides. And b squared is 3/4. Square root both sides. and I get that b equals root 3 over 2. So the length of this side down here is root 3 over 2. Okay, those are our two special right triangles. So now if we take all three of the ideas that we have, reference angles, coordinates as distances, and special right triangles, I can look at this circle here, which we called our unit circle, and take my special right triangles and copy them over. So if I take this triangle and I copy it, and I come over here and I paste it, this triangle is going to map to this spot on the circle. And we knew that this distance was 1, the radius was 1, so this was root 2 over 2, and this was root 2 over 2. That makes this coordinate right here, because our coordinates are distances, the point root 2 over 2, comma, root 2 over 2. That is one of the points on this circle. I'm going to find two more. I take this 30, 60, 90. I'm going to copy and paste it. When I drop that down here, this length was a half, and this length here, so this length down here on the bottom, was root 3 over 2. So this is the point root 3 over 2, comma, 1/2. Then I'll take one more of those triangles, and this time I will rotate it, yeah, like this, and I'll flip it. Nope, that'll accomplish the same thing I just did. Ha. There's the one I want. This triangle here is basically the same one, only now these coordinates are going to flip. So this is 1/2, comma, root 3 over 2. So I can find these coordinates on this unit circle based on having a triangle that's 30 degrees, 45 degrees, or 90 degrees. Now what I can do, I'm going to get rid of all these measurements in here. Take those three little triangles that I just grabbed and group them and copy and paste them and flip this over, or reflect it actually. And I can get three more coordinates. Here, all the x values flipped. This x value here copies to this x value over here, but it gets a negative sign, so it's negative root 3 over 2, comma, 1/2. This one flips, so it becomes negative root 2 over 2, comma, root 2 over 2. And this one will also flip to negative 1/2, comma, root 3 over 2. I could do that again with all the bottom angles. Take this, flip it over, find these points here, and then do that one more time. Flip it over and reflect it now. And that way I can get what we call a unit circle that's going to look like this. I'm going to simplify how that looks a little bit. But we have all of these angle measures and all of these special right triangles and right triangles. And this is on the back of your calendar. And this way we can see, I know why this is like that. We can see both sides, or see all of these angles and spots. So we're going to fill this in now and get all these angle measures, both in radians and degrees. . This spot right here was 30 degrees. this was 45, this was 60. That makes this 90. And now I'm going to start adding 30 degrees here. This is a travel limit of 30, so 30 plus 90 gives me 120, making this 135 and 150, excuse me, 150. Here's going to be 180, 210, I'm just going to count by 30s for a while, 240, 270, 300, 330, and 360. I've gone all the way around the circle. I'll fill in those last missing gaps. 180 plus 45 is 225, and 270 plus 45 is 315. So there are all of our angle measures in degrees. Next we'll go through and we'll do them in radians, and the radians can be a little bit tougher for us to get our head around, so think about it this way. We know that a whole entire circle is 2 pi radians. Well, the whole entire circle is 2 pi radians. I'm going to put that here at 2 pi because that's a whole circle. And then half a circle is pi radians. And a quarter circle would be half of that. So if half a circle was pi radians, another half of that is pi over 2. So 90 degrees is pi over 2 radians. I can go half again. Half of 90 degrees is 45 degrees, so half of pi over 2 radians is pi over 4 radians. So I know that 45 degrees is pi over 4 radians. And at this point I'm going to count by pi over 4s to get all my 45 degree measures. So I got this one. This is pi over 4. So this would be 2 pi over 4. I'm counting another 45. That's 2 pi over 4, which is really pi over 2. So this one right here would be 3 pi over 4. The next one is 4 pi over 4. The next one is 5 pi over 4. The next one is 6 pi over 4, which is really 3 pi over 2. 6 pi over 4 is 3 pi over 2. Then we have 7 pi over 4. And 8 pi over 4 is 2 pi. This gives us pretty quick conversions. Now we can see, if we look real closely, that 225 degrees is 5 pi over 4 radians, or that 315 degrees is 7 pi over 4 radians, or that 3 pi over 2 radians is 270 degrees. You can find conversions between these degrees and these radians quite quickly. Next we will do the 30 degree radian conversions. If 90 degrees, that's what this is here, this says 90 degrees, not very well. If 90 degrees was pi over 2 radians, I divide that by 3 to get 30 degrees. So pi over 2 divided by 3 or times a third is pi over 6. So 30 degrees is pi over 6 radians. So I'm going to count by pi over 6s. And I think I'll change color for this. This right here was pi over 6. So then I go another 30 degrees, that's 2 pi over 6, and 2 pi over 6 is really pi over 3. Then another 30 degrees is 3 pi over 6, or pi over 2. Then another 30 degrees is 4 pi over 6, or 2 pi over 3. Then another 30 degrees, so this here is the next 30, I'm skipping the 45s. 4 pi over 6 goes to 5 pi over 6, and 6 pi over 6 is pi. Then 7 pi over 6, then 8 pi over 6 is 4 pi over 3, and then 9 pi over 6, and 10 pi over 6 is 5 pi over 3, and 11 pi over 6. And we filled out the radians of our unit circles. So now I know that 4 pi over 3 radians is really 240 degrees, and I've got a quick conversion. And 5 pi over 6 radians is 150 degrees. And the last thing to do is fill in these coordinates. Filling in the coordinates makes sense if you think about this in terms of special right triangles. This right here was a 45, 45, 90, and we knew that that was 1, root 2 over 2, and root 2 over 2. This was a 30, 60, 90, which was 1, 1/2, and root 3 over 2. Well, then this coordinate here is the point 0, 0, but as I start moving up the circle, first I traveled 30 degrees, which means that my x-coordinate was root 3 over 2, and my y-coordinate was 1/2. This is literally the coordinate, the point, root 3 over 2, comma, 1/2. The y value is 1/2, or halfway up the circle. The x value is root 3 over 2, or whatever that decimal is. We've traveled that far along the circle. The next one is a 45-degree angle. This one here is 45 degrees. That's root 2 over 2, because we're talking about this here. So that becomes root 2 over 2 and root 2 over 2. Then we take this triangle here and we kind of flip it over. This triangle gets flipped. So this is 1/2 root 3 over 2. This is the point 0, 1. In fact, we can do these right angle points and flat line points pretty quickly, 0, -1. Now that I have the first quadrant all done, all the points in between get filled in really quick. So like this point here is going to map over to this point here, but the x value flips. It's -1/2, comma, root 3 over 2. So this point here will also map over to this point here, but the x value flips. So it's negative root 2 over 2, comma, root 2 over 2. This will become negative root 3 over 2, comma, 1/2. And this is filling in really tight now. Like it's tough to see everything and squeeze it all in there. In fact, maybe I should just go to one screen at this point and see how that looks. Yeah, I can clean that up a little bit. Negative root 2 over 2. So this is negative root 3 over 2, comma, 1/2. And I can just keep reflecting points. This point bounces to here. So now the x value isn't changing. The x coordinate doesn't change, but the y value flips. Negative root 3 over 2, -1/2. Negative root 2 over 2, negative root 2 over 2. And then -1/2, negative root 3 over 2. Over here, the x values will be positive, but the y values will be negative. We're in quadrant 4 now. So the x values are positive, 1/2, root 2 over 2, root 3 over 2. The y values are negative, negative root 3 over 2, negative root 2 over 2, -1/2. So we found the coordinates of all these points based on all these angles with a circle that has a radius of 1 that we call the unit circle. This has so many uses. There's a couple things I want to talk about it, and then we'll wrap up. First of all, here in quadrant 1, the x values are positive and the y values are positive. Here in quadrant 2, the x values are negative, the y values are positive. Down here in quadrant 3, the x values are positive, the y values are, they're both negative, both x and y are negative. And over here in quadrant 4, the x values are positive, the y values are negative. And that's stuff that you know from a long time ago. You've learned about your graphing. The most useful thing about this, however, is probably finding sines and cosines very quickly. Think about how we talked about this triangle here, which I've got so much stuff drawn on it now it's almost tough to see it. But this triangle here. This coordinate, we realized, had a y value and an x value, but to find that coordinate, it was 30 degrees in here, we had to do the sine, or we can do the sine of 30 equals y over 1, because the radius is 1. So it's really just sine of 30 equals y. Well, that means that the sine of 30 is root 3 over 2. Because we found this y coordinate. That's the point, root 3 over 2. This, I'm sorry, 1/2. Come on, Grant, pull it together. The sine of that 30 was 1/2. That's the y value. The y value here was 1/2. If you want to find a sine value of a theta, sine of any angle on your unit circle, it's just the y coordinate at that point. And if you want to find an x value of any angle, it's the cosine. X is a cosine. So when we say here that x is positive, that really means that the cosine of theta is positive, and that the sine of theta is negative. Because cosine means x and sine means y. So if I ask something like, what's the cosine of 150 degrees? Well, 150 degrees is right here. This one here is 150 degrees. For cosine, that's the x value. So the cosine of 150 is really negative root 3 over 2. And if I go to my calculator and I check that, I do the cosine of 150, and I get that, and I do negative root 3 divided by 2, and I get the same thing. So I can find cosines and sines of these particular angles incredibly quickly, and these particular angles are incredibly useful. If I wanted to find the sine of 210 degrees, well, 210 degrees is here, the sine is the y value, and the y value is negative 1/2. And if I wanted to find the cosine of 3 pi over 2 radians, well, the 3 pi over 2 radians is here, cosine is the x value is 0. So the cosine of 3 pi over 2 is 0. I'll put my calculator in radians to try and show this to you. The cosine of 3 pi divided by 2 is 0, just like I said it would be. Lots of things to wrap up here. So the idea is a unit circle can give us sines and cosines of common useful angles by looking at coordinates. Root 3 over 2, root 2 over 2, and 1/2 are the coordinates we're going to be working with the most. You will memorize this, you will learn it, you will love it, you will rely on it. It's a beautiful, beautiful thing. That was the unit circle. Thanks for bearing with this one.